Hello, everyone. My name is Jeff John Siracusa, and I'm a mathematician at Swansea University. I'd like to tell you today about a subject that's near and dear to my heart, a subject called tropical geometry and tropical algebra. This is a subject that's right at the cutting edge of new mathematics being developed. And the exciting thing is that in this session, I'm going to take you from the mathematics you've been doing at school, the abstract algebra and arithmetic that you've already learned and come to master. And we're going to go from there all the way up to some brand new mathematics, something that is right at the research forefront. So to start with, I'd like to show you a few slides here. Is this your stereotype of what a mathematician looks like? Somebody who's a bit nerdy and gets overly excited. I'd like to try to bust up this stereotype a bit. So probably you imagine that studying mathematics at university might look a little bit like this. Huge blackboards filled with unintelligible symbols, and you probably feel like this. But then people get a little bit more interested when they find out that you can make some of this stuff. For instance, this guy, Jim Simons, I got to meet him once. He was a research mathematician at University of California in Berkeley. And then he realized that he could use some of the abstract differential geometry that he had been working on and apply it to the stock market. He became the most successful hedge fund investor in the world. And last I checked, which was probably about a decade ago, he was worth this huge amount of money down here. That's a 5 with a lot of zeros on it. It's probably worth a lot more than that now. They were averaging around 70% returns most years. So mathematicians don't always look like this. I first learned about tropical mathematics from Diane McLagan, who was a mathematician at Warwick, a professor there. Before that, my PhD supervisor was this woman, Ulrika Tillman. Now, being a mathematician is a little bit like being a Jedi or a Sith. There's always a master and an apprentice. So I was her Padawan, and now I'm a fully fledged Jedi master, a mathematician. And I have several of my own Padawans, which we in mathematics call students who are working on their PhDs. Doing a PhD means becoming an apprentice and eventually graduating up and being a full master of your subject. Tropical mathematics, people always say, where does the name come from? Well, the name more or less comes from this guy, Imre Simon, who passed away about a decade ago. He was born in Hungary to a Jewish family. He did his PhD in Canada, and then he lived and worked most of his life in Sao Paulo in Brazil. What does this have to do with the word tropical? Well, here's a picture of Brazil, and if you look down in the middle of the screen there, you see the city of Sao Paulo, and there's a little dotted line which is labeled the Tropic of Cancer. I don't know where I got this map from because that's actually the other tropic, the Tropic of Capricorn. The Tropic of Cancer is in the northern hemisphere. And the Tropic of Capricorn runs right through the northern suburbs of Sao Paulo. So people said, oh, Imre Simon, he invented this mathematics and he lives in the tropics. And then other people said, oh no, actually, University of Sao Paulo is below the tropic. It's outside the tropical region between the two tropic lines on the globe. So he wasn't really in the tropics. And then other people pointed out that actually his home was in the northern suburbs. And the northern suburbs were north of the tropic, and his university was south of the tropic. So his daily commute took him across the Tropic of Capricorn. And so it's in honor of Imre Simon's daily commute that we named this subject tropical mathematics. What are these tropic lines? Well, just a bit of geometry here. As the Earth goes around the sun in its orbit, the North Pole and the South Pole aren't pointed straight up and down. They're tilted a little bit. And that tilt stays the same as the Earth goes around. In the summer, the Earth is in a position so that the northern hemisphere is tilted towards the sun. This is northern hemisphere summer. And on the June solstice, it's maximally pointed towards the sun. And the Tropic of Cancer is the line around the Earth where the sun is going to pass directly overhead. If you're further north than that, then as we well know, living in this northern country, the United Kingdom, the sun never really gets close to being overhead. It passes at some angle over the horizon. But if you stand exactly on the tropic line, that's where you have to be for the sun to be overhead. And the same thing happens in reverse in the December solstice in the southern hemisphere. So the Tropic of Capricorn, the one which went past Imre Simon's house, is where you'd have to stand in December for the sun to pass directly overhead at noon. Here are some of the objects that we tend to study in tropical geometry. I won't tell you much about these, but I thought I'd show you some nice pictures. There are lots of interesting questions about these weird looking things. And coming back to the subject of mathematics and money, here's a picture of a venerable institution, the Bank of England. The Bank of England is the bank for banks. It's basically there to make sure that our whole financial sector keeps running so that banks don't run dry of funds and become unable to administer people's savings accounts and business accounts. The Bank of England, for the last decade now, more or less, has been using tropical mathematics on a daily basis to more or less keep our economy alive. So tropical mathematics is very important. Now, we're going to start with a little bit of a warm-up here as we get into the mathematics. Here are 3 mental mathematics problems: 107 times 3, 309 times 2, and 10,015 times 5. So have a go at each of these. Try to do it in your head as quickly as you can. I'll count to 15 and see if you can do it that quickly. Okay, so the first one, we get 321. And I'm guessing that you used a particular technique in doing this. You broke it up, I'm guessing, and did 100 times 3 plus 7 times 3. Same for the next one, 309 times 2, you probably did 300 times 2, that's easy, 600. And 9 times 2, 18, 618. The same for the last one. We probably get 50,000 plus 15 times 5, which would be 75. So here's the calculation, the way I'm guessing most of you did it. Right? We used an important property here, the fact that we could break a number up into 2 pieces and then multiply the 2 pieces by something and then add it up again. And this property that we use to do these math problems in our head has a name. It's called the distributive property. In the abstract, it says that A times B plus C is equal to A times B plus A times C. And this is something which is supposed to be true whenever A, B, and C are any numbers at all. Now, I'm going to switch modes of presentation here, and I'll start writing on my whiteboard. Right, you've all probably been told that it's not a good idea to compare apples and oranges. But what we're going to do now is enter into a world of abstract algebra where we are going to add and multiply apples and oranges. So I have here on my display some rules for arithmetic with apples and oranges. So these are the rules that we're going to be working with. The idea is, in the algebra you've probably learned up to this point, it was all about, we've got some numbers and some letters, and you try to probably solve for x, or solve for x and y. But as you go to university, there's a transition, and what we mean by algebra changes. And algebra becomes a subject where you get to create a world where the rules of arithmetic bend to your will and do what you want. And then you explore that world. You explore what happens. What are the consequences of those rules? So in that vein, we're going to do exactly that. Here are the rules, and let's start playing around with this arithmetic. So here I have some problems, problem 1, problem 2, and problem 3. Let's have a go at problem 1 here. So we've got apple plus orange times apple plus orange. Let's look at the middle bit here. in the middle bit, we've got an orange times an apple. And up here, I see orange times apple. I'm assuming that orange times apple is the same as apple times orange, is an apple. So that thing in the middle, I'll write A for apple and O for orange because it's too laborious for me to draw apples and oranges all the time. That thing in the parentheses is an apple. And then I see that I have an apple plus an apple. So those two together are going to give me an apple using this rule up here. And then finally, I have an apple plus an orange. An apple plus orange using this rule here is an orange. So the whole thing is equal to orange. Or I'll just write O for short. Let's try the second problem. We've got orange times apple, which gives us, if I use this rule up here, that's an apple. Then I multiply it by an orange again. Apple times orange is still an apple. Then I add to that this orange over here, and I'm going to use this rule, which says apple plus orange is orange. So the result is an orange. And the last one, if we look at what's in the parentheses, apple plus apple, using this first rule here, is an apple. Then I'm going to multiply that by an orange. And orange times an apple is, if I look over here, this rule, orange times apple is apple. I'm going to add to that this apple here. So apple plus an apple using this rule is still an apple. And then I'm going to add to that this orange here using this rule. And the result of the whole thing is orange. Okay, not too bad. Let's try a few more. Okay, now I've got to scroll down and we've lost the rules, but I'll talk you through it here. Apple squared. What does apple squared mean? Well, apple squared means apple times apple. And if you look up at the rules, apple times apple was an apple. So that apple squared is an apple. Orange squared, this one here, means orange times orange, which was an orange. And orange cubed was orange times orange times orange, which is an orange times an orange squared. Using the rules again, that's an orange. So we've got an apple plus an orange plus an orange. Adding the apple to the first orange, these two here, gives us an orange. And then we add an orange to that. And using the rules above, or since orange plus orange was equal to apple, this rule here, the result is we get an apple in the end. Okay, let's try this second one. 3 times an apple. What does that mean? Well, 3 times an apple means take 3 apples and put them together. So this is apple plus apple plus apple. And using the rule, every time you add 2 apples together, you get an apple. So the first 2 added together is an apple, and then add that to the third one, and we have an apple. So the 3 apples is an apple. What about the 7 oranges? Let's look at that. This gets a little bit more interesting. 7 oranges is orange plus orange plus, I won't write them all out. We've got 7 oranges added together. Well, can't work that out just yet. So let's simplify things first. If I have 1 orange, it's an orange. If I have 2 oranges, that's orange plus orange. Remember, these are oranges, not zeros. 2 oranges is, I need to go back and look at the rules here. 2 oranges is an apple. 2 oranges is an apple. Okay, let's keep going here. 3 oranges is, well, it's 2 oranges plus 1 more orange, which is the same thing as the apple that we just worked out, plus an orange. And then you look up back at the rules, and you see that there's a rule that says apple plus orange is an orange. Okay, so let's see what's going on here. The first one was an orange. The second one was an apple. The third one was an orange. Let's try one more here. 4 times oranges is, well, this is the same thing as 2 times orange plus 2 times orange. And both of those we worked out were apples, and apple plus apple is an apple. Oh, so it alternates. Orange, apple, orange, apple. You can keep on going and you find that n times orange is equal to, well, there are 2 possibilities. It is an apple if n is even, and it's an orange if n is odd. Oh, that's interesting. We found a pattern here. Let's move on. Now, the next thing we want to do is come back to that distributive rule that we saw before. The distributive rule said that A times B plus C is equal to AB plus AC. Now, the question I'd like to pose and address is this true for apples and oranges? Right. Is the distributive rule something that we can apply to apples and oranges just as well as we can apply it to numbers? Well, to test it, we need to make a little table here. So A, B, and C in this distributive rule are allowed to be any of the things that we can add and multiply. If we're talking about traditional arithmetic, that means A, B, and C are numbers. But in the apple and orange world, that means A, B, and C are apples and oranges. So let's make a big old table here. We've got A, B, C, and let's enumerate all the possibilities here. They can be apple, 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 orange, apple, orange, apple, apple, orange, 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 apple, apple, orange, apple, orange. Keep going here. Orange, orange, apple, and finally orange, orange, orange. Should be 8 possibilities. I can tell because there are 2 possibilities for A times 2 possibilities for B times 2 possibilities for C. So 2 cubed is 8. So we've got 8 different possibilities for what A, B, and C can be. And in each of those cases, we want to check what is A times B plus C, and what is AB plus AC. So let's just, I won't work through all 8 of the possibilities. I'll leave that for you as an exercise if you want to try it. But let's try a few of these. I'll write it in red here. Let's try this one here to start with. So A is an apple. So I've got an apple times orange plus orange. Now, if you look back at the rules, you see that orange plus orange was an apple. Remember that orange it alternates. If you add up an even number, you get an apple, and if you add up an odd number of oranges, you get an orange. And then you look back at the rules and you see that apple times apple was apple. Now let's try the other side. AB plus AC means we've got an apple times an orange plus apple times orange. And both of those, apple times orange, or apples, and when you add two apples together according to the rules, you get an apple. So the important thing to observe here is that having calculated this side and having calculated this side, we find that we have an A here and an A here. These two things are equal. Now, we could go through and fill out this entire table, and maybe I'll leave that for you to check if you're curious. And you can find out by filling out that table if apple-orange arithmetic satisfies the distributive rule or not. Okay. That's a question that you can answer. This is the beginning of doing mathematical research. Now, so far we're doing apple-orange arithmetic. But what does this relate, how does this relate to numbers? Well, I'll give you the, I'll give you the reveal here. Apple, we can think of as corresponding to the number 0. Right, that's now the number 0 rather than an orange. And orange, we can think of as corresponding to the number 1. And now apple-orange arithmetic, if you write this in terms of zeros and ones, turns into, well, apple plus apple turns into 0 plus 0 was equal to an apple, that's 0. 0 plus 1, this was apple plus orange, turns into apple plus orange was an orange, so that 0 plus 1 is equal to 1. Orange plus orange is equal to apple. That turns into 1 plus 1 is equal to 0. And let's do the multiplications. Apple times apple turns into 0 times 0 was equal to 0. Apple times orange was apple, so that turns into 0 times 1 is equal to 0. And orange times orange equals orange, from our original rules, turns into 1 times 1 is equal to 1. So this first rule, 0 plus 0 is 0, that makes sense. The second rule, let's see, second rule, 0 plus 1 is equal to 1, that makes sense. 0 times 0, that makes sense. 0 times 1 equals 0, that's something we're familiar with. 1 times 1 equals 1, that's something we're familiar with. And this one here is a little bit odd if you haven't seen it before. This is something where our apple-orange arithmetic is deviating from the way numbers, natural numbers or real numbers normally work. But this looks like what's called modulo 2 arithmetic. Which means 1 plus 1 is 2, but the remainder of 2 on division by 2 is 0, so we put that 0 in there. And so the apple-orange arithmetic was really modulo 2 arithmetic in disguise. That's how I cooked up this apple-orange arithmetic for you to play with. But now, let's move on to tropical arithmetic. Right. The topic here is we're supposed to be talking about tropical mathematics, so let's do some of that. So our numbers now, the things that we're going to add and multiply, are still going to be numbers. So we're still working with ordinary numbers, but now what we're going to do is change what the operations are. So I'm going to give you some new rules for doing arithmetic with numbers. And the new rules, instead of calling them plus and times, just to keep us from getting confused, I'm going to draw a circle around it. These are called a circle plus or O plus, and circle times or O times. There's just slightly different symbol to keep track of the fact that this is meant to be a kind of addition operation and a multiplication operation in a different universe, a parallel bizarro universe where the rules are completely different. So what are the rules here? Well, let me tell you what this circle plus and circle times are. A circle plus B is going to be the maximum of A and B. And A circle times B is going to be A plus B, right? This looks a little bit confusing, and it is a little mind-bending. We're using ordinary addition as our tropical version of multiplication. Okay, let's do a couple of examples of this. So let's start with 8 circle plus 7. That means take the maximum, the bigger of the two. I get 8. Let's try something a little bit more involved. 1 plus 2 plus 3 plus 4 plus 5 equals, well, adding all of those up using this O plus operation, the tropical addition, I just take the maximum of 1 and 2, whichever one is bigger, 1 or 2, that's 2. And then I take the maximum of 2 and 3. And then I take the maximum of 3 and 4, and so on. And so the result of this is 5. Okay, easy enough. Let's try some multiplications. 5 tropical times, O times 3. Remember, this means 5 plus 3, which is 8. 10 tropical times 10 is equal to 10 plus 10, which is 20. And let's try one that mixes the two together. 1 tropical times 2 tropical plus 3 tropical times 4 tropical plus 5. And let's work this out. So the 2 tropical plus 3, this bit here, is the maximum of 2 and 3, that's a 3. The maximum of 4 and 5 is a 5. And then these tropical times operations are pluses. So 1 plus 3 plus 5 is 9. Okay, let's try a few more of these. Let's try 4 tropical plus -2. This is simply the bigger of 4 and -2. That's of course going to be 4. What about 4 tropical times -2? 4 tropical times -2 is 4 plus a -2, which is the same thing as 4 minus 2, that is 2. And let's try, how about 5 tropical times -2? This is 5, take away 2 is 3. Okay, let's rearrange things a little bit. 3 tropical times 2 is 5. How about 5 tropical divided by 2? Right. So here I've introduced a new operation that we haven't seen before, circle divided by. But let's try to take a guess of what this operation could mean. Circle divided by is going to be, well, it's going to be the opposite of circle times. When we multiplied by 2, that meant add 2. So when we divide by 2 in the tropical sense, we should take away 2. So this should be 3. Let's try 7 circle divided by 3. That means take away 3 from 7. So that gives us 4. Okay, now here's the puzzle. In ordinary arithmetic, we had the nice property that for any number a times 1 is equal to a. Okay. You can multiply anything by 1 and it doesn't change it. Is there a number b such that a tropical times b is equal to a for all numbers a? Okay. So we can use ordinary multiplication by 1 and not change a number. Is there something that we can tropically multiply by to not change any number? Well, a tropical times b is equal to a ordinary plus b. And if we want that to be equal to a, then this implies that b had better be 0. So what we're saying here is that a tropical times 0 is equal to a. So tropical multiplication by the number 0 doesn't change anything. Now let's try the same thing for addition. So in the ordinary world, a plus 0 is equal to a. In the tropical world, is there a b? Well, let's use a different letter. Let's call it c, such that a tropical plus c is equal to a. There's the question. Well, a tropical plus c is the maximum of a and c. And that's equal to a if and only if c is smaller than or equal to, what happened there? Smaller than or equal to a. Right. So for this to be true for every single number a, c needs to be pretty small. Right? If it's going to be true for 1 and 5 and 10 and a million, then c has to be less than 1 and less than 5 and less than 10 and less than a million. That's easy enough, but c equals 0. But then I also want it to work for a equals negative 10. If a is going to be negative 10, then c has to be less than negative 10. And if a is going to work for a equals negative a million, then c has to be less than negative a million. And we keep on going, and we see that c has to be less than any number. Now, there isn't any number that's less than every single other number, except we can use our imaginations a little bit and create one. And the number we're going to create is negative infinity. This is not one of the existing numbers that we were already allowed to work with. It's an extra number that we're going to add in to this system. Now, let's come back to the distributive property. So, is tropical arithmetic distributive? This is the question that we're going to try to find out. Let's have a look at this. The distributive property, remember, said A times B tropical plus C. And we want to compare that with and see if it's equal to A tropical times B tropical plus A tropical times C. So it's not quite so straightforward. You have to, you can't make a table in this case. You have to think a little bit more. So let's think about this. On the left-hand side here, we have, well, this is really A plus the maximum of B and C. Okay, this is just translating the tropical arithmetic into ordinary notions. And on the right-hand side here, what I've got is the max of A and the maximum of A plus B and A plus C. So if I calculate on the left, which one is bigger, B or C, and then I add A to that, do I get the same thing by adding A first and then taking the bigger one? And the answer is yes. Okay. We can find the bigger of B or C and then add A to it. Or we can add A first and then choose the bigger one, and it doesn't make a difference. You'll get the same result either way. So tropical arithmetic is distributive. That's good. We like distributive arithmetic because it lets us do things like this mental arithmetic tricks. It makes doing arithmetic a lot easier if we have a distributive rule. Right, now let's go on and do a little bit more abstract algebra here. So the next topic is polynomials. Polynomials. So first, some preliminaries here. If I have the variable x, then I'll write x squared to mean x tropical times x. And if I write x cubed, what I mean by that is x tropical times x tropical times x, 3 x's multiplied together. And if I write 4 x squared, this means, now this is a little bit confusing here. What I need to tell you what I mean by that 4 in front. What I mean is take the number 4, tropically multiply it by x times x. Right. This is, note, this is not the same as, this is not equal to x squared tropical plus x squared tropical plus x squared tropical plus x squared. Okay. These are two different things, and I need to tell you which one I mean when I write 4x squared. It's potentially confusing, but as long as I'm clear, then we should be okay. Okay, so now let's look at a polynomial in general, f of x. And let's suppose we have something like x cubed tropical plus 3x squared, 3x tropical plus 1. Right, now one of the things you can do with a polynomial is plug in values. So let's try what is f of 0. Well, f of 0 means I take 0 cubed plus 3 tropical times 0 plus 1. So I just plug in 0 for the x. 0 cubed means 0 tropical times 0 tropical times 0. So I'm adding 3 zeros up. I get a 0. The 3 tropical times 0 means 3 plus 0. That gives me a 3. And the last one is a 1. and I'm taking the maximum of those three. So I get 3. Let's try another one. F of 1 is equal to, let's plug a 1 in for the x. So 1 cubed, tropical plus 3 times 1, tropical plus 1. 1 cubed mean 1 tropically cubed means 1 tropical times 1, tropical times 1, which means 1 plus 1 plus 1, which means 3. 3 tropical times 1 in the middle there is a 4. And the last term is still a 1. And now I'm tropically adding those 3 up. I take the maximum, and I get a 4. You can do one more just to play with this. Let's try f of 2. So this is 2 tropically cubed plus 3 tropical times 2 plus 1. 2 tropically cubed is 2 plus 2 plus 2, 6. 3 tropical times 2 in the middle here is a, that's really 3 plus 2, that's 5, and the last one is still a 1. And so the answer now is a 6. Okay, so now we've got some practice doing tropical polynomials. Let's let's play around with some of these things. So the fun of tropical geometry is turning the algebra into geometry by doing things like looking at the graph of a function. So let's finish up here by looking at a couple of graphs. We're going to plot the graphs of some polynomial functions. So f of x is equal to, let's do the simple polynomial 2x. So to plot a graph, I'm going to plug in lots of values. So to start with, let's plug in the value 0. So 2 tropical, this is a tropical times in there. 2 tropical times 0 gives me, oh, that's 1, that's 2, 3, and so on. So 2 tropical times 0 means my plot is starting here. Let me draw the plot in red. So it starts here. Now let's plug in 1, 2, 3, and we'll see what happens. Okay, when I plug in 1 for x, I have 2 tropical times 1, which gives me a 3. When I plug in 2 for x, I have 2 tropical times 2, which gives me a 4. And 3 gives me 5, that's up there. And you can see that the graph looks like this. Straight line. And this is a line of slope 1. And that slope corresponds to the fact that we have x is really the same thing as x to the 1. So the slope comes from reading off the exponent. And the intercept here is equal to 2, which is that coefficient there. So the coefficient gives us the intercept, and the exponent gives us the slope. Well, that's all well and good when we have something like 2x or 2x squared, something fairly simple. Just to write this out, 2 tropical times x. This is really 2 plus x. Oops. And of course, you know how to plot the graph of that. That is a linear function of slope 1 with intercept 2. Let's try another one now. Let's try f of x is equal to x squared tropical plus 1, just to make it a little bit more interesting. So x squared plus 1 here, we need to set up our plot. Let's see. When I plug in x equals 0, I have the x squared here gives me a 0, and I'm tropically adding 1, so I'm taking the maximum of 0 and 1, so I'm at a value 1. When I'll write out some values. F of 0 is 1, f of 1 is, when I plug the 1 in for x squared, I get 1 tropical times 1, which is 1 plus 1, so I get a 2, and then I'm taking the maximum of 1 and 2, so I get a 2. F of 2, this is going to turn out to be a 4, and basically what happens is when we take the maximum of these two terms here, the x squared term is always going to be the bigger one, as long as x squared is bigger than 1, which means bigger than x has to be bigger than a half. Try to remember tropical arithmetic. So at 1/2, if x squared is less than, if x is less than or equal to a half, then the 1 is the term that gives us the maximum. So we've got a straight line out here, and we've got a line here of slope 2 now. I've drawn it so it looks like slope 1, but it's actually slope 2. Right, so let me just rearrange this a bit. This is saying that x squared plus 1 is really the maximum of 2x, and this is ordinary times here, and 1. So this first part here is a line of slope 2 going through the origin, and the second part is the constant line 1. So the first term is that line of slope 2, and the 1 is this part here. And we're taking whichever one is bigger, which means draw them both and then the plot of the function is at each point take the higher one. So on the left, the 1 is the higher one, and on the right, the line of slope 2 is the higher one. And we ignore this stuff here and this stuff here. So we can do one more of these. Let's try the following. F of x is equal to 3x squared tropical plus x. So let's look at our plot here. Now, we can be a little bit more intelligent about this. The x here is giving us a line of slope, 1 and intercept 0 by what we said before. So this is a slope 1 line through the origin. And the first term here is giving us a line with intercept 3, and the slope is 2. So that's a steeper line. And so when we take the maximum of these two, over on the negative side, we've got the higher one, and then like this, and it's got this little kink in it right here. And to the right, nothing interesting happens. It just looks like a line of slope 2 and intercept 3. And the only interesting part is this little bend here. Right. So now I'm going to give you a little bit of a glimpse of where this all goes. Finding roots of, finding the plot of a tropical polynomial is interesting because it's a little bit like plotting plotting the graph of a regular polynomial. And one of the things you do with regular polynomials is you try to find where the zeros are. So with a regular polynomial in the ordinary world, you might have a plot that looks like this. And you say, here's a 0, and here's a 0, and here's one. And we found 3 roots, and this might be something like an x cubed plus some other terms. In the tropical world, we don't have as many places where the function crosses the x-axis. And instead, the role of zeros turns out to be these kinks, these bends in the graph. And there's a whole theory built up around the relationship between finding roots of ordinary polynomials and finding the bends in the graph of one of these tropical polynomials. And that is the starting point of the whole subject of tropical geometry. So I hope that I've given you enough of a glimpse of this subject to start playing around and try some calculations of your own in tropical geometry. One thing that, if you're curious, you can try is see if you can factorize some polynomials in the tropical world. Factoring polynomials in the tropical world is very different from factoring polynomials in the regular world. And in particular, you might find that sometimes there are polynomials that can be factored in 2 very different ways in the tropical world, which is completely different from what happens in the ordinary world, where if you factor a polynomial, that's it, you're done. Those are the factors. So there's a little bit of research that you can play around with on your own in your own home. I'm going to thank you for listening to me there, and you'll have a chance to ask some questions now. Thank you very much.